Okay, so these are the three stats of ideal gas law, or when it comes to thermodynamics. Because imagine if you want to have some in your process, okay, in the industry, in the process, when you want to do produce something, okay, and your substances, they are in the form of fluids, or we call it as gas. So the property of the gas is determined by these three stats. Okay, stat STATE, pressure. What is the pressure of the gas? Okay, so what is the volume of the gas? If the bigger the volume, then it will affect perhaps the pressure also. Okay, and the temperature also will affect the property of the gas itself. Okay, so these are the three most important stats that will affect your gas. All right. So Boyle's law says that your pressure is inversely proportional with your volume when your temperature is kept constant. Okay. And Charles' law says that the volume is directly proportional with the temperature when your pressure is kept constant, just like the hot air balloon, right? So when you heat up the air, what happened? The air expanded, the volume expanded. Gay-Lussac law say the pressure is directly proportional with the temperature when your volume is kept constant. So this is just like your pressure cooker at home. The volume is kept constant, because the size of your pot with the cover, okay, it's kept constant. That's why the size is constant, the volume is constant. When you continue to heat up, what happened? The pressure inside the cooker increases. So due to the assistance of your pressure and also your temperature, the food get cooked faster. So these are the three laws that involve with ideal gas law. So what happens when we combine all these three together? We get the ultimate, okay, ideal gas law. Okay, PV equals to nRT. I think you have learned in your chemistry also. So this is ideal gas law. Recall P stands for pressure, and this pressure stems with your Bernoulli equation. It must be absolute pressure. So what is absolute pressure? Absolute pressure is inclusive of your atmospheric pressure plus the gas pressure. And pressure in the unit of Pascal. V stands for volume in the unit of meter cube equals to nRT. N is number of mole. Okay, so this is the SI unit when we want to measure the how many mole of the molecule. So this is the SI unit, yeah. R stands for universal gas constant. Okay, so this is a constant, and if you look at the values and the unit, 8.31 joule per mole per Kelvin. So all these, they are in SI unit. Because your constant is already in SI unit, so that's why your other parameter here, your PV, your N, your T, must also be in SI unit. Okay, so 8.31, this is a constant. And T is the temperature. See, the SI unit of temperature is in Kelvin. So please highlight the K to remind yourself, because this is a common mistake that always forgotten. Okay, things that it's commonly forgotten, because we are so used with degrees Celsius. Okay, so but remember SI unit, They are in Kelvin. So what is actually ideal gas? So for ideal gas, there are some, in order to be an ideal gas, there are some requirements. Okay, so firstly, the atom of the molecule of the gas, it's moving randomly. Okay, they do not move in the same direction, but they move randomly. Okay, so imagine you have a space with gas molecule inside and they are moving randomly. Yeah, and exert no long range forces on each other. Okay, so there is no forces between your molecule and molecule or your atom with atom. So they are freely moving and they are independent of each other. Yeah, so they can be seen as a particle that is individually point-like. So there are no forces between each other. So when you learn in your chemistry, there could be what type of forces, van der Waals or whatsoever. That kind of forces is not existing in ideal gas. So when they are independent, somehow it's easier to do calculation. Oh, so physicists, they likes to do things like this. We want to make complicated things easier for us to do calculation. So we will assume for ideal gas, there is no we say relationship or no force in between atom and atom, and they occupy a negligible volume, meaning that the atom is so small that the volume of the atom is negligible compared to the whole space that occupied by this ideal gas. Okay, so if you look at the size or the space, this one, okay, the boundary that I draw with blue color, this is the volume that occupied by the whole ideal gas, and compare with the size of the small atom here. Okay, so the blue color and the green color size, if you compare, the green color is so small as compared to the blue color region that we can neglect the green color. Okay, so this is ideal gas. Okay, firstly, the direction they move randomly. And secondly, there is no force between atom and atom or molecule with molecule. And finally, their size is very, very, very small until you can neglect the size. Okay. So there are some further explanation about ideal gas law. You can watch this YouTube video. So I will post this on the annotated slides on Moodle. So when you do your revision letter, you can watch them through, okay, to reinforce your understanding about ideal gas law. Okay, so for all the ideal gas, they also obey the kinetic theory of gases. So when they obey these kinetic theories, we can interpret the pressure and the temperature of the gas in terms of microscopic variables. Okay, we can look into them, into the very small component. Okay, so what are the assumptions that we make to the kinetic theories? So basically, it's the same as ideal gas, but there are two more that you have to take notes. Yeah? So we assume that there are a lot of molecules in the gas and they move randomly with variables of speeds. Also, when they move randomly, the speed will be different. So perhaps atom 1 meter per second, atom 2 1.2 meter per second, atom 3 2.3 meter per second. Okay, they are moving randomly, freely inside. And the size of molecule is very small as compared to the distances between them. Yeah, so this means also your size of the molecule is very small as compared to the volume occupied by the ideal gas law. All right. You imagine if the distance between them is very far away, doesn't it mean that the volume occupied by the ideal gas is also very big? Then you can have a set, just like if you have a small home, if your house is very small, and there are 10 of you in the house. So the distance between you and your team member are very close. But if you have a big house and with the same amount of 10 members in the house, isn't it? You and your family member will be separated quite long. I mean, the distance between you and your family member will be quite far away. Okay, so same goes with this. The size of the molecule of your of the gas is very small as compared to the distance between them. Okay, yeah. All right. And the third one, molecules obey the law of Newton's mechanics. No forces between them. Yeah, just now I already mentioned there is no relationship between atom and atom. Okay, when they are moving through it, except when they collide. So when you collide, you feel the pain. So that is the force. Or when you collide, imagine two ball, they bounce against each other. What happened? They rebound. So this is the force. So as long as you do not meet, yeah, but once you meet, there is a force between you. All right. So when they no forces between the no forces. No forces between the atom, huh? Okay, until they collide. And so these three are the same as ideal gas law. The fourth one, so we talk about collision. So when they collide, their collision are called as perfectly elastic collision. So remember what is perfectly elastic collision? When they meet, then they do not move together. Huh? They do not stick together, but they move separately. So this perfectly elastic collision, there is no energy loss. Where is my point? Okay. Perfectly elastic collision with no energy loss, meaning that the kinetic energy is conserved in this collision. Okay. And all the molecules in the gas are identical. So all the molecules are the same. So you cannot have a mixture of gas inside. So these are the 5 assumptions. Firstly, they move randomly with different speed, different direction, different speed. The size is very small as compared to the total volume occupied by the ideal gas. Okay. The third one, no forces in between them except collisions. So during their collision, the collision is perfectly elastic collision. And finally, the gas are identical, or the molecule are identical. Okay, so I want you to memorize and see how much you can memorize. And scan this QR code, or I will give the link in the chat later for you to type what you have remembered inside the Google Docs. Have you shared the QR code? Sorry, scan the QR code. Week 4, yes. Next week, next Monday, we will be having our midterm. So no class on Tuesday. Monday, you have your midterm. And your Tuesday, you take a rest first. Wednesday, we have our lecture 5. Yeah. So I divided lecture 5 into 2 parts because lecture 5 it's very long. And starting lecture 5 and onwards, you will be learning new things which you haven't learned in high school before. And somehow you are moving into, or you are being promoted into a I would say a more challenging field of physics, moving to electrostatics, magnetism. All right. So based on the previous experience, it takes some time for you to digest. All right. So I decided to divide topic 5 into 2 topics so that you could 2 parts so that you could have more time to digest topic 5. Once you are okay with topic 5, then it's easier for you to move on to the remaining topics. So please be ready for Wednesday, next Wednesday. Yeah. Oh, I know you have midterm for chemistry on Tuesday, right? You take some time to rest first. And we do not have class for Wednesday and Thursday, this Wednesday and Thursday, because you need to do your proposal submission. So I'm giving you time to complete your proposal and also to do some revision for both physics and chemistry. So you can take the time for physics slot for all this, yeah? But after the midterm, please, forgot about the past, but we work hard for our future. So topic 5 is your future, which is your final. Monday is exam. 15 November. I wrote on Moodle, right? 15 November. And also on the briefing slides. Monday exam. It's already been announced during the earlier briefing slides. And I posted on Moodle because I worry if some of you forgot. I believe you watched through the videos. So let's see. Wow, your word is very pretty. Yes. So the assumption for kinetic theory, random motion, very good. So moving in, random motion, different speed and different direction. The size is very small compared to the distance between them, correct? The molecules obey the laws of Newton's mechanics, means no force between them except during collision. Okay, 3 and 4 are the same. So I highlight these two, means they are the same. No forces between them except they collide. And the fourth one, all collision does not result in loss of energy. Very good. So this is a perfectly elastic collision. The energy here, remember, it refers to kinetic energy. If you are unsure, so it's kinetic energy. Okay, someone can help me to type or put a bracket for kinetic in front of the energy. Yes, thank you, Taufik. You put a bracket. So just for your information for you to know what types of energy, how come collision no loss of energy? So you know it's kinetic energy. Okay. And the fifth one, all gas molecules are identical. Your molecules are identical. So you cannot have a mixture of this is hydrogen gas, and later on another we have a helium gas. No, there is no mixture of gases. Okay, your molecule must be the same. Very good. Thank you for your help in recalling the kinetic theory. So you have to remember, yeah, these are the 5 assumptions. So let's move on about the calculation. So remember we have PV equals to nRT. N. So this N refers to number of mole, 1 mole. But what is 1 mole of atom or 1 mole of particles or 1 mole of molecules? Yeah, 1 mole consists of 6.02 times 10 to the power of 23 particles. So when we talk about 1 mole of gas, so inside this 1 mole, there are this many amount of particle. 6.02 times 10 to the power of 23 particles. If I have this amount of money, I don't want to work anymore. Okay, so 1 mole is consists of a lot more of particles. So particles can be atoms, can be molecules. Okay, so we use particles to represent them. All right, so this 6.02 times 10 to the power of 23 is called as Avogadro number, or in the unit of big capital N subscript A. Okay, so you can use this for unit conversion later. Okay, 6.02 times 10 to the power of 23 particles in 1 mole. Okay, I know you learned in chemistry before, just a revision. So let's work on this practice question. So first 2 question is more on explanation. Yeah? So we have a piston or a cylinder. Yeah, and the piston is there. So the gas inside is an ideal gas. The volume is fixed. Yeah. Oh no, the cylinder is, the piston is here to fix the volume. And the gas inside is moving freely. So explain how the molecules of the gas produce a force on piston when they collide on it. So there are molecules inside here. And remember, they are moving freely and randomly. So definitely there are times when they will collide with the piston. So how the force is applied on the piston? So look at the explanation. So it is due to Newton's second law and third law. Okay, it's not being mentioned in our topic 1, but you learned it in your semester 1, or this is just for your information. So when they collide with the wall or piston, what will happen? Okay, according to Newton's second law, they experience a change in momentum. So this change in momentum is the impulse, or we call it impulsive force. So they just like impulsive force, just like when you are driving and you bump into something. So the amount of force that you receive when you bump into something, this is what we call as impulsive force. Okay, so just imagine you are the atom of gas and this piston is the wall. So when you bump into the wall, what will happen? You receive an impulse in your body. Okay, so this is from the Newton's second law. And according to Newton's third law as well, when you bounce into something, you apply the force on, because you go and bump into the wall, right? So you apply the, let's say, 10 Newton of force on the wall. So at the same time, the wall will give you a reaction. This is what we call as the reactive force. So when you bounce into the wall, you feel the pain. Why? Because the same amount of force is being given back from the wall to you as well. Okay, so this is what we call as the equal and opposite force, or we call, or another word is reactive force. Reactive force. All right, so if this is about the explanation of why there is force during collision. Okay. The second question. B1. Okay, so the gas in the cylinder has a volume of this. B1. Explain in terms of frequency of collisions by the molecule of the gas, how the pressure remains constant as the volume increases. All right, so how the pressure remain constant when volume increases. Okay, so we know that when volume increase, let's say you have a space with 4 particles of ideal gas. When you increase the volume with the same amount of particles in the space, what happened? The chances of collision decreases, right? The chances of collision decreases. So when chances of the collision decreases, what will happen to the pressure? The pressure is supposed to be decreased as well, right? Okay, so when you increase the space with the same amount of molecule, or sorry, same amount of particle, we call the number of molecule per unit volume decreases. Okay, this number of molecule per unit volume decreases. Okay, so let's say this is 4 molecules, oh sorry, 4 particles. And let's say the volume is 1 meter cube. Divide by 1 meter cube. So we get 4. Number of molecule per unit volume is equals to 4. And let's say when we increase the volume, we make it into 2 meter cube with the same amount of molecule, or sorry, particles, divide by 2. So our number of molecule per unit volume is equals to 2, isn't it? Decreases. Okay. So because of the increases in volume but the same amount of particles or molecule, the number of collision decreases. The frequency of collision decreases. Sorry. By right, the frequency of decrease, the frequency of collision decreases. So when that decreases, by right, yeah, your pressure should decrease as well, isn't it? However, what happened here is because there is a rise, in order to maintain the same pressure in your ideal gas, what you should do? There should be a rise in temperature. What happened? So when your temperature increases, it will cause your molecule to move faster because they gain energy now. They are more hyperactive. So they move faster with higher kinetic energy and speed. So when they move faster, the frequency of collision increases. Okay, so meaning that the increase in the speed of the particles or the molecule offset the decrease of this one of number of molecule per unit volume. So that's why your number of collision now, or your frequency of collision now is the same. So when your frequency of collision is the same, meaning that your pressure will be the same. So what will happen if you would like to increase your volume but keeping your pressure constant, then you have to increase the temperature. All right, so this is the explanation of how could you increase the volume of the gas at the same time still keeping your pressure at the same. Okay, so next move on to the calculation. So given that the gas in the cylinder has a volume, this is your volume, 1.6 times 10 to the power of negative 3 meter cube at temperature of 30 degrees Celsius. This is T. But look at the unit. Remember, SI unit for temperature is Kelvin. So the gas is heated to a temperature of 90 degrees. So let's assume this one as T1, this one as T2. Expands under constant pressure. So pressure is constant. 1.1 times 10 to the power of 5. calculate the volume of gas at 90 degrees Celsius. So we want to calculate what is our V1. So from our ideal gas law, PV equals to nRT. So we could, if we take out the constant, these two are constants because they are the same gas, yeah. Just the time is different. So we can have PVT, right? P1 V1 over T1 equals to P2 V2 over T2. This is our ultimate calculation for ideal gas law. Okay. So in this case, given that your pressure is constant, so meaning P1 equals to P2. So we can cancel off P at the both sides. Now we have only V1, T1. V1 over T1 equals to V2 over T2. So let's sub in the values. V1 is 1.6 times 10 to the power of -3. Divide by T1, 30 degrees Celsius, convert to SI unit, plus 273. V2 is the unknown that you need to find. T2, 90 degrees Celsius. So solve with your calculator. 1.9 times 10 to the power of -3 meter cube. Okay. So just now we look at the number of mole. Now let's look at the pressure. Yeah. So why is P constant? It's mentioned in the question, huh? It's given in the question. The volume is expanded under the condition of constant pressure, huh? So that's why for this scenario only, P is constant. Huh? So move on to our pressure. So remember, I said pressure, there are two types of pressure. Yeah? One is absolute pressure and one is gauge pressure. Okay. So atmospheric pressure, absolute pressure equals to gauge pressure plus atmospheric pressure. So atmospheric pressure is the pressure that is on the earth. Okay, so on the earth we have this atmospheric pressure, and this atmospheric pressure is equals to 1 atm. 1 atm is also equals to 1.01 or 1.013 times 10 to the power of 5 Newton per meter square. So this Newton per meter square is also equals to Pascal. So you can also write them in 101.3 kPa. Okay, so usually if we want to keep them in 3 significance figures, so just put 1.01, yeah. But you use 1.01 or 1.013, it's also acceptable. Okay, gauge pressure is the difference pressure difference relative to atmospheric pressure. Okay, so if you want to find is equals to absolute pressure minus your atmospheric pressure. Okay. So if you want to find absolute pressure, you must plus your atmospheric pressure. P naught stands for atmospheric pressure with the gauge pressure. Okay. So let's look at a question. Given that the tire is filled with a gauge pressure with 200 kPa, kilopascal at 10 degrees Celsius. So after driving for 100 kilometers, the temperature within the tire raised to 40 degrees Celsius. So this is our T1, this is our T2. So this is our PG1. What is the pressure with the tire now? Okay, so the pump, if you go to the petrol station to pump your tire, the meter that you see on the pump is actually in gauge pressure. So for this one, you would like to look for what is the gauge pressure for point 2. So from our PV1, PVT, 1 equals to P2, V2, T2. In this case, what is being held constant? Your volume, right? Because they are trapped with the size of the tire, so your volume is constant. So when your volume is constant means V1 equals to V2. We can cancel off V on the both sides. So plug in the values. P1, we have 200 kilo. This is only gauge pressure, but remember it must be in absolute pressure. So plus 1.013 times 10 to the power of 5, or you can put both with the prefix together, 101.3 K. Divide by temperature, 10 degrees Celsius, SI unit plus 273. So P2 is what you need to find. 40 degrees Celsius convert to SI unit. P2 is 333 kilopascal. So what is gauge pressure at point 2 equals to the absolute pressure at point 2 minus your atmospheric pressure. So absolute pressure at point 2 is 333 kilo minus 101.3 kilo. Yes, we get 232 kilopascal. Okay. So basically, for this one, extracting the information is not difficult, but usually students get wrong because of SI unit. I remember the memes that show by one of your group, the Tom and Jerry, and Tom is going to catch the Jerry, but sitting on the toy trend. But before reaching the Jerry, there is a big hole because of the SI unit. Huh? So there, keep the means in your head. Do not be the Tom. All right? Yes, you can. You can. Huh? Because we are not penalizing you with the significant figures or the decimal point. Yes, you can get to the exact amount, because when you go to degree later, yeah, they will want you to use that figure also. Okay, so starting that, but if you want to keep the significant figure, yes, you can. But again, my advice is don't go to until 7 or 8 decimal point. That is truly impossible. Okay, you might want to keep your final answer to the reasonable, or we say the reasonable measurement that you can measure. Okay, two decimal point. I would say 4 decimal point is the maximum. Do not go until 7 or 8. This is also one thing that I would like to share. Okay, usually how do we catch students cheating in the exam is when both of you go up to 7 and 8 decimal points, and these 7 and 8 decimal points are exactly the same, which is super impossible. Okay, but I hope your batch don't do this. Please don't do this to me. Okay, and other lecturer also. Okay, so solution here. Okay, so ideal gas law. Just now we learned about PV equals to nRT. So this is the most common ideal gas law that we use. But if you further expand this equation with Avogadro number, right? Remember just now Avogadro number is in how many particles, number of particles divided by mole, right? So if I would like to find the number of particles, let's say if number of particles is given by big capital N here, number of molecules, divided by number of mole equals to Avogadro number. So if I would like to find the number of particles is equals to number of mole times number of mole times Avogadro number, isn't it? So rearrange. What is N? N is equals to number of particles divided by Avogadro number. So let's put this in here. Okay. So according to Boltzmann constant, small capital K is equals to gas constants divided by Avogadro number. So if I combine these two together, what will I get? PV equals to capital N K T. Okay, so here I develop another equation for ideal gas law. With your P still the same, which is the absolute pressure, V volume, N now is number of molecule. K, small capital K, is Boltzmann constant, 1.38 times 10 to the power of negative 23 joule per Kelvin. And T is the temperature in Kelvin. Okay, so this is another ideal gas law or ideal gas equation that you can use. So usually when do you know which one to use? So for your case, you just look at the question, the information that is given to you. If they give you number of mole, then you just use PV equals to nRT. But if they give you number of molecules, then you can use this one with Boltzmann constant. So the good news is all types of constants will be given. So you don't have to worry, do I have to remember? No need lah. All this will be given. Okay? So why do we need to know all this? Because they are related with the pressure and kinetic energy of the ideal gas. So this is a well-derived equation for the pressure of the gas. Okay, so 2/3, yeah? So why 2/3 is because of the 3-dimensional consideration. So I won't go through the derivation because it's quite complicated, but if you want to know more, I can show you the explanation, okay? But for your syllabus, you don't have to know how to derive them. Just remember, must be 2/3 or 3/2, okay? So for pressure, it's 2/3 times N over V. So KE, this one means this is average. The bar sign on top of KE, This is the average kinetic energy. So we know that the pressure is proportional to number of molecule per unit volume. Number of molecule per unit volume. Number of molecule is big capital N, right? Volume is V. So put them in equation is P directly proportional to N over V. So whenever we want to convert a directly proportional into an equation is equal, there must be equal with a values of constant here. So in this case, this constant here is represented by 2 over 3. This is a constant value. 2 over 3 times N divided by V. And also is directly proportional to the kinetic energy. So we know that they are moving at different speed. So we can't choose only one speed of a molecule. That will be truly unfair. So what we do is we have to take the average value. Okay, so it is directly proportional with N over V and also directly proportional with kinetic energy. So when you put them into equation, remember the directly proportional is equals to a constant, then your variables. So this is what we get, is 2 over 3. So from this equation, to find the average kinetic energy, what you get? You get 3 over 2, correct? Okay, P here, move 2 over 3 N over V to the other side, you get 3 over 2 V over N. So we have 1 over N, 3 over 2 PV. Okay, so from our PV equals to N KT. Move your N to the other side. 1 over N PV. Isn't it equals to KT? So from here, 3 over 2 KT. So this is how we get this one, yeah? So kinetic energy, average kinetic energy is equal to 3 over 2 KT. Okay? So that is kinetic energy. What is total kinetic energy? This is average kinetic energy, average for one molecule. What is total kinetic energy? So total kinetic energy, so you can put a T, subscript T at the bottom here, equals to the total number of the total molecule, number of molecules times your average kinetic energy, and you get, expand them, N times 3 over 2 KT. Right. So this 3 over 2 KT, you have 3 over 2 N KT. So this NKT, isn't it same as your ideal gas law, ideal gas equation? PV equals to NKT. And PV is also equals to nRT, isn't it? So that's why we can have 3 over 2 nRT. All right. So this is the finding of calculation for kinetic energy. So when we want to calculate kinetic energy, at the same time, we will have to calculate the velocity as well. So the velocity here, because we are referring to the average velocity only, so we call this as root mean square speed. So this root mean square speed, root means the root square, whereby you need to do root square, means is the average, and square is to the power of 2. So whenever we have something like the average, this means the average of the speed. When we root square the square of the average of something, then this is what we call as root mean square. Okay, is another terms for average values, but it's only involved when you root square a square. Okay, so you will encounter these RMS values in, I guess, topic 10 later, yeah, about root mean square. So it actually means average, but it's only applicable to when you root square values of a square, and that is an average values, yeah. So deriving from our average kinetic energy equals to 3/2 kT, expand this one, kinetic energy equals to half mv squared. So since this is an average value, so your velocity also an average value. So simplify this one to find only your v value, yeah. So you will get your value as 3 kT divided by m root square. So your VRMS is equals to this one. Okay, so why we call this as RMS? Because in order for you to get your V value, basically you have to root square your square value, isn't it? So that's why we call this as root mean square. And remember, for your M is the mass, right? So your mass is atomic mass unit. So what do we mean by this one? Remember, in your chemistry, you learned about molecular weight, correct? So for example, oxygen. The molecular weight for one atom oxygen is 16. Is it? So for oxygen molecule, since there are 2 of them, so there are 32. So in here, atomic mass unit means this 32 must comes with the U values. So what is the actual mass of the oxygen now is 32 times the U value 1.66 times 10 to the power of negative 27. All right, so that is the actual mass value of this one. Remember, for this, you must times with the atomic mass unit. Okay, so this root mean square speed is actually, like what I said before, is the average speed of the molecule here. Because every molecule, they are moving at different speed. We have V1 until V8. So in order for us to do calculation, we will take the average values. Okay, so that's all about part 1. Let's take a break of 5 minutes before we move into our part 2, which is the first law of thermodynamics. Yeah? 5 minutes, come back at 9:03. 9:04 lah. So let's move on to second part. So second part is about thermodynamics. Huh? So just now we only look at ideal gas law. So it's about the gas itself and the particle inside them. All right. So now when it comes to thermodynamics, it's the whole thing. Now we look at the big picture now. Okay. So what you have to know about the first law of ideal gas? The first law of thermodynamics. You learn about zero zero law of thermodynamics in semester 1. So what is first law? What does first law say? Yeah? So for first law of thermodynamics, there is one important term that you have to know, which is internal energy. So this internal energy is the overall energy of everything, of all the atoms and molecules inside the whole system. So the system here is our gas. Okay, in physics, now for ideal gas law, the system is our gas. So the internal energy means the hambalang, I mean like the overall, all the energy, the kinetic and potential energy of the particle. So remember just now we learned about our total kinetic energy of our ideal gas is equals to 3/2 nRT, right? So this one is also representable as the internal energy because it already cover all types of energy in the ideal gas. So for our ideal gas, remember we said that there is no forces in between gases and gases, correct? So, but they are moving freely with different direction and different speed. And when we sum up all this speed together, okay, this is what we call as internal energy. Okay, so however, in fact, that is only for ideal gas law. Okay, for thermodynamics, it's applicable to all types of gas, even though it is not ideal gas. So for this case, instead of kinetic energy that we mentioned previously for ideal gas, now it also consists of potential energy. So they are representable by the same equation, which is 3/2 nRT. All right. So if it is about first law of thermodynamics, remember, it also covers gases other than ideal gas. Okay, so that's why instead of kinetic energy, we also consider potential energy, but the values are the same, which is 3/2 nRT. And remember, from our equation, PV equals to nRT equals to nKT. So by replacing nRT with nKT, we can get 3/2 nKT or 3/2 PV. So usually we will use this and this. Okay, depends on what information that you obtain from the question. Okay, so review quiz, the total energy of an ideal gas depends on volume, pressure, temperature, or all of above. What is your answer? A, B, C, D. What is your answer? Yes, very good, Jeff. Because PV equals to nRT, so also equals to 3/2 PV. Okay, so we have volume, pressure, temperature, so all of above. So all these will affect your ideal gas. Okay, so apart from internal energy, another terms that you have to know about this is work done. So for work done for thermodynamics, you learn about work done is equals to force times distance, right? So for thermodynamics, it's about the expansion or compression of the gas. So it is given by pressure times the change in volume. So remember, for thermodynamics, there is work done when there is change in volume. So when we say change means final minus initial. So when there is change in volume, there will be work done. So for this one, there is sign convention. Sign convention for in order for us to do calculation. So the sign convention, the first sign convention given is when expansion, then there is work done. Why? Because expansion means the work is done by the gas. Okay, the gas is doing the work. The gas has to push the wheel of the piston for expansion. So the work done is done by the gas. So sign convention is positive because you are doing work. During compression, there is no work done by the gas, but the surrounding is doing the work on the gas. Or we say the piston is doing the work on the gas by compressing the gas. So work done is negative. Okay, so expansion means your final velocity, final volume is larger than the initial volume. Compression means your final volume is smaller than the initial volume. Okay, so why do we need to know this? Because of our first law of thermodynamics. First law of thermodynamics says that the internal energy is equals to Q minus W. Q is thermal energy, or we say the heat. Okay, so when the heat energy, or when the heat is applied to the gas, okay, so the gas will absorb the heat and use it to do work. So after minusing the amount of heat to do work, then the remaining energy is called as the internal energy. Okay, so that is, put a delta in front means change in internal energy. So all these, each parameter here, they have their own sign convention. So I would want you to, my advice is memorize them, because it will not be given in, this will not be given as the formula sheet. You won't be given, and you are expected to know the sign convention. So positive means there is an increase in the temperature, or we say increase in internal energy. So why is it increase in temperature? Remember, internal energy equals to 3 over 2 nRT, isn't it? Your N and R, they are constant. So the only variables is temperature. So if the change of internal energy is a positive, means your final internal energy is larger than initial internal energy, isn't it? So meaning that the final temperature is actually larger than the initial temperature. Then you will get such values. Okay, so if you get a positive delta U, means there is an increase in temperature. If you get negative delta U, means there is a decrease in the temperature. As for Q, stands for heat or thermal energy. If it is positive, means the heat is absorbed by the gas or absorbed by the system. Our system is the gas here. If it is positive, means absorb heat. If it is negative, means heat lost to the surrounding. Positive means the gas is doing work, so expansion. Negative means the gas is not doing any work, or the work is done on the gas. Someone else is doing the work on the gas, so compression. So take 10 seconds to memorize this, and I want you to write them down on the Google Docs just now. Okay, 10 seconds already. Now, scan this or go to the same link just now and scroll down to write the sign convention. If you accidentally close the Google Docs, Scroll down. Yes. Huh? Yeah, the first column under definition, you have to write down what does the symbol representing. Delta U is change of internal energy. So Q is thermal energy, or you can put a bracket heat. Okay. So yeah, you can help me to put a bracket heat. Just to remind you, the Q is the same heat that you learned in your first semester. Q equals to MC delta T. Huh? So is heat. W is work done. Okay, work done by gas. Huh? So positive increase in temperature, correct? No? Negative for delta U means decrease in temperature. So Q, thermal energy absorbed by gas, correct? Thermal energy lost to the surrounding. W, work done by the gas on the piston, very good. Huh? Work done on the gas, okay? So perhaps for W, put a bracket for positive means expansion. Put a bracket expansion for W. Negative, put a bracket compression. Huh? Because usually the question will not tell you, oh, the work is done on the gas. The questions will tell you what is the change in volume, or they will say the piston is compressed, the gas is compressed, the gas is expanded. Okay, so just put that for your more information. Huh? Okay, so seems like you are very good. Now let's move on to the calculation part. So just now we have already calculated until here. So we just need to visit this question. What is the work done by the gas? So given work done is equals to pressure times change in volume. So given we have a constant pressure, 1.1 times 10 to the power of 5, what is the change in volume from our previous question? Okay, V2 1.9 times 10 to the power of negative 3. Okay, V1 1.3 times 10 to the power of negative 3. Yeah, so this is V1. And from our calculation, V2 1.9 times 10 to the power of negative 3. So P 1.1 times 10 to the power of 5. Change in pressure, this is final. This is initial, so 1.9 times 10 to the power of negative 3 minus 1.6 times 10 to the power of negative 3. So we get 33 joule. Okay. So this is how we find work done. So positive also tell us that this is an expansion. Oh, the sign convention will not lie to you as long as you put the correct sequence. Yeah? Now let's try an example of first law of thermodynamics. So the gas heat is equals to 2005. It's added to the system, so means now the heat is absorbed. So this is a positive value because according to sign convention, heat absorbed is positive. And 1008 of joule work is done on the system. Done on means negative, right? So this is negative work done. What is the change in internal energy of the system? Okay, so your equation delta U equals to Q minus W. All right, so from our information, Q is positive work done, so positive 2005. W is negative work done, so we get negative 1018. So put the values in your equation. Q equals to 500 minus Q negative 1800. So we have 4,300 joule. Okay, so what would be the internal energy? Okay, the change in internal energy if now 2005 is added of the system. So Q is equals to positive value. And now the work is done by the system. So your work done also equals to positive now. So applying the same equation, Q is positive, so 2005 minus work done positive 1008, and we get 700 joule. Okay, so different sign convention, huh? Your answer will be different, even though the value is the same, but look at the sign convention. Then you just plug in the values. Yeah. All right, so I will complete this part first. Then I will leave the calculation to the tutorial workshop session. So for thermodynamic processes, there are 4 types of processes. So remember them. Isobaric means constant pressure. Isochoric means constant volume. Isothermal means constant temperature, and adiabatic means there is no heat transfer. Okay, so constant pressure means initial pressure equals to final pressure. Okay, so how do we remember this one? Iso means same. Remember isometric means same on both sides. So iso means same. Okay, bar is a measurement of pressure. It's one of the unit for pressure. So iso bar means same pressure. So this is how you could remember for pressure. Okay, move on. Isothermal. T, remember, it stands for temperature. So means T, there is no change in temperature. If there is no change in temperature, likewise, there will be no change in internal energy. Remember, when we say change in internal energy equals to U, final U minus initial U, expand the equation of your U, 3 over 2 nRT, right? So it will be 3 over 2 nR T final minus T initial. If there is no change in T, then no change in U as well. Okay, so isothermal, remember the T is the same temperature. Okay, so there are 3 iso, 1 adi. Huh? 3 iso here refers to the change of or the constant value of the 3 steps PVT. So only this adi which is different from them. Remember, this one is only for Q, means there is no heat transfer. Q equals to 0. All right. So the remaining iso, how this is also taught by your seniors. Okay, they told me. Okay, means isobaric means constant pressure. Isothermal means constant temperature. So the third iso is iso C, stands for clever. So iso clever. So in Mandarin, we usually say when you want to boast about something, we call it as 吹水. 吹水 means you are blowing water, like you want to boast about something. So iso clever means he is blowing water. So water is related with volume. So this is how he remember for this one. Isochloric related to clever. So I am choi soy means blowing water. I'm boasting. So water is volume. So this is his way of remembering these 4 types of thermal processes. So you can have your own way too. All right. So I give you also 10 seconds to remember, and I want you to go back to the Google Docs just now to complete the third page. Oh, already completed so fast. Very good. Okay. Yeah. Isobaric is very fast. Constant pressure. All right. So isochoric, constant volume, so no work done. Remember, no change in volume, no work done. Isothermal, no change in temperature, so no change in internal energy. Adiabatic means no thermal energy transfer. So just not to let you get confused, help me to put a bracket after thermal energy, put them as heat. Okay, because of this thermal energy, sometimes students might get confused. Oh, isothermal means no thermal energy, then Q equals to 0. No, yeah. Remember, thermal energy is heat. So isothermal, look at the T in front. That is T equals to constant. Okay, so that means this picture, this the picture for the means is also contributed by your seniors. They go and look for all the means and put inside here. Okay. So I guess I will just stop here, and I will further move into the explanation of each process. And the calculation. Okay, this will be the long question types of calculation. So when I say this, you will be expecting to encounter one calculation of this in your part C of your midterm. Oh yeah, I would like to make some changes in your midterm description. Since we have only 3 topics in our midterm, so you look at here on the Moodle page, the pattern of the questions for your part A, there will be 5 multiple choice questions. So these 5 questions, each question only 1 mark. So it will be a very basic conceptual question. Part B, instead of 4 questions now, only 3 short questions, 3 structure questions, and each question's 5 marks. And finally, optional 2 long questions. So there will be a total of 3 long questions given to you, 1 from each topic, and you only need to choose 2 topics or 2 questions out of the 3. So 1 question, 10 marks. So I guess it's same as your physics 1, yeah? Okay, the first 2 parts, part A and part B, just answer directly into your Moodle. But part C, you have to answer separately on a piece of paper, or if you have tablets, you can just write on your tablet and submit to me the document. Okay? So if you have question, you can still ask me. So any question regarding your lecture? Yes, you can. Oh, yes, you can. If you have time, yes, you can. I welcome you to try all the questions. For the marks, initially, okay, for the marks, I will choose 2 best marks to be included as your final marks. But this one only for foundation. Why? Because I appreciate your effort in attempting all the questions. Usually for my open book exam, it's not that easy. So I appreciate your effort, but do not bring this practice to degree, because during in degree, only first 2 questions will be marked. This is the message passed from degree lecturer to me, because they always say foundation, we spoil you all. But no, what I do is I appreciate your effort. So for me, I will choose the best 2 questions that you have attempted. Okay, but for degree, remember, they will only choose the first 2 questions that you place. Okay, you position them. So if let's say you try 3 questions, you get full marks for question 3, and you only get 5 marks for question 1 and 6 marks for question 2. So they will only mark the first 2. Okay. Any question? Apart from midterm, any question about today's topic? No, huh? If no, then that's all for today. I guess you have to move to your next class. Yeah. Okay, bye-bye. Thank you. See you later or tomorrow. Welcome.